Okay, hello everybody. It's time now to start exploring the system K in a bit more detail. We're going to use truth trees in particular. I'll mainly use the tree method that was developed by, I believe it was by James Garson in his book Modal Logic for Philosophers. That was certainly the first place I saw it. I think his tree method captures very well the concept of modal logic in a very kind of clear and common sense way. So we'll be using that method. There are others, and I'll explore them later. So first of all, we have the tree rules of propositional logic, the standard tree rules of propositional logic, and I'm assuming these are all totally familiar. If you've never seen trees for propositional logic, I've got a couple of videos about them. So these are the standard tree rules. The difference is here is we put boxes around them, and those boxes represent our worlds. Now obviously our worlds aren't doing much here. We've just sort of put them around these trees. Worlds become relevant when we look at how to use the box and diamond operators. Okay, so we have 4 new rules, and I want to take possibility first. If you have possibly A, then you need to draw an arrow to a new world and derive A in that world, because possibly A means that WO accesses some world at which A is the case. Okay, so you draw an arrow to a new world, derive A in that world. The red here represents what you derive, and the black represents what you start with. Now, the rule for necessity is a bit different. The rule for necessity says that if you have an arrow to another world, then you can use necessity to derive A in that world. If you have an arrow and another world already there, you don't draw the new world in. You have to wait until the new world becomes available. So, I mean, again, black shows what you start with. So, in the case of possibility, you can draw in the new world. You have to draw in the new world. In the case of necessity, you have to wait until the new world has already become available. Right, with not necessarily A, here you draw the new world in. For not possibly, the world needs to be already there. And this is perfectly sensible when you consider that not necessarily is just possibly not, and not possibly is just necessarily not. I think I went over this in my first video on modal logic, but so if you don't know what I'm talking about, watch that. So really you only need these first 2 rules, but it's helpful to have all 4. Okay, it is extremely important that you don't confuse these rules. It will mess up everything if you do them wrong. So only use necessarily and not possibly when you already have an arrow to another world. Only use them when you already have the world there, and only use possibly and not necessarily when you draw in a new world and add it, and you have to draw it in. Okay, so don't get that wrong. You have to wait until the new world. Have to wait until the new world's there for necessarily and not possibly. For possibly and not necessarily, you have to draw a new world in. Okay, finally, you can use necessarily and not possibly any number of times. So let's say you draw in a new world. You can apply these rules again. So if you've had another sort of possibly whatever, and you've drawn in another world from WO, then you can use necessarily A to derive A and not possibly A to derive not A again and again and again. You can do them over and over. I've said before that when you do truth trees, it's good to tick formulas as you decompose them, so that you can keep track of what you've done. But you shouldn't really tick the necessarily or not possibly, because if you create a new world, you can use them again. Right then, another thing that's worth mentioning is that just as it's a good idea to apply non-branching rules before you apply branching rules, generally you should apply all the rules you can within a world before creating new worlds. So that's just a sort of general tip there, and again that could mess things up if you kind of get that wrong. Okay, so those are the sort of basic rules. It's time to actually do some truth trees. Okay, here's one. If necessarily if P then Q, then if necessarily P then necessarily Q. That's an argument with no premises there. So first of all we need to draw our world, then we have to assume the negation of the conclusion, and that gives us a false conditional. So this is the standard truth tree rules. We've got a false conditional, that means we have a true antecedent and a false consequent. Okay, and I'm starring the formulas as I use them in this particular example, but I probably won't do it in the other examples. It's a good idea to use stars to keep track of what you've done, but it's kind of difficult to add the stars on PowerPoint, so I don't think I'll be using them too much. Right, well, again here we have another false conditional, so that means true antecedent, false consequent. Right then, now this is interesting. We have applied all of our standard rules for propositional logic. So now we've got this not necessarily, and from this we can derive not Q. But remember, first we have to draw an arrow and add in a new world. Okay. Well, now what? Well, we've got necessarily P here, and because we have this arrow to world 1, because that's already there, we can now use the necessarily rule to derive P at W1. Now, although I've just used the necessarily rule, I'm not going to star the formula, because again, it doesn't really matter in this example actually, but if you were to draw another world from WO, then you could use necessarily P again. Okay then, right, so we've got necessarily if P then Q. So in W1 we can derive if P then Q. Now I think at this point the most rudimentary natural deduction skills should tell us where this is going. But let's complete the tree anyway. If we have if P then Q, then we know that either P is false or Q is true, and in either case we have a contradiction. Right then, so that's our tree complete. That's done. Nothing more to do there, and that means that our original argument is valid. Since it's an argument with no premises, it's of course just a logical truth, and it's actually one of the more important logical truths, because it's part of the traditional axiomatic way of defining the system K. Not really important to us, but just for sort of reference, this formula here is called distribution, because I guess the necessity is distributed across the conditional. But that's one of the traditional axioms that's used in the axiomatic formulation of K, which I'm not going to be looking at, but yeah, that's an important formula. Okay, I want to look at another example which should illustrate some important things to bear in mind when constructing trees of this sort. So this is our argument, possibly P and possibly not Q, therefore not, if not necessarily Q, then necessarily not P. Right, so first of all we'll draw our world, and then we'll add our premise and the negation of the conclusion. Obviously the negation of this conclusion would be not if not necessarily Q, and so on, but by double negation that just gives us the conditional, the true conditional. So I'm going to skip the double negation steps to save space. So then we have our conjunction, from which we can easily derive not P, possibly P, sorry, and possibly not Q. Then we have our true conditional, Either the antecedent is false or the consequent is true. Again, I'm skipping the double negation step. And that's it for the standard propositional rules. We now have to create some worlds, and it's at this point that that problems might emerge. So let's say we focus on the left branch. Well, we've got possibly P up here, so that means we can draw an arrow to a new world deriving P, right? And we've got necessarily Q, so we can now derive Q since we've got a world open. Now at this point you might think, okay, well look, we've got necessarily not P in WO. WO accesses W1, so we can put not P in W1 like that. No, 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 no. That's a big mistake. Do not do this. Do not do that. The reason is that we're on the left branch of this tree, and necessarily not P is on the right branch. Remember that all we know from this conditional is that one of these two options is the case. They might not both be the case, so we have to treat each branch as separate. Okay, each branch is separate. Worlds from one branch cannot draw on formulas from another branch. Each branch is independent, so we cannot derive not P. Okay, right. So let's continue our work then. Right. So you might think, okay, well we've got another possibly statement here, and for each possibly statement we need to create a new world. So you draw an arrow to a new world, and you put not Q in it, and then you've got, of course, necessarily Q here, and that gives you Q, which is a contradiction, so the world closes. But look, that's it. That's all we can do on this branch. We've used all our rules, we've used all the rules that we can use, and yet one of our worlds, this world here, is still open. We haven't derived a contradiction in this world. And of course it doesn't matter what we do over here, each branch is separate, so nothing we do over here matters. We are never going to close that world. That world is going to remain open, and that would suggest that our original argument is invalid. Again, a fatal mistake has been made. The problem is with this whole world here, this entire world here. It should not have been put there. Okay? Right. When you open a new world from a particular branch, the world's opened from the other. When you open a new world from a particular branch, and you then open other worlds from that branch, those other worlds need to be put below the first world to be opened in that branch. Okay, they need to be put below each other. You need to stack the worlds as if they're in a branch themselves. So it should look like this. Okay? And you know, it is because these worlds, remember, are part of the same branch. They both come from the same branch. So these worlds are not evaluated completely separately. We put W2 under W1, and we then evaluate them together. Now, this isn't to say that contradictory formulas in different worlds mean that we can derive a contradiction. You know, just because we have P in one world and then not P in a world below it, that doesn't mean that we have a contradiction. But what it does mean is that if we derive a contradiction in either of these worlds, the whole branch closes. You're right? So the fact that we have a contradiction in W2 means that the status of W1 becomes irrelevant, because they are taken together. When they're from the same branch, we evaluate them together. There's a basic sort of rule of thumb that you can think about here. Separate branches mean separate worlds, right? So each branch is independent. Separate branches mean separate worlds. But different worlds on the same branch are placed together. Worlds from the same branch must be evaluated together. Right, so those are two perhaps common mistakes. I hope that that's cleared them up. Now let's finish the tree. So we've got another branch here, and we've got possibly P up here. So we open a new world, put P in there. Of course, we've got necessarily not P, so we can derive not P in our new world. That's a contradiction. The world closes, the branch closes. Of course, we could, if we wanted, open up a new world and put possibly Q in it, but there'd be no point because we've already got a contradiction here. There's already a contradiction on this branch, so there'd be no point doing that. Right then, and that means that our whole tree is closed. It's all done, and that means that our original argument up here is valid. Well, I hope that was helpful. We'll have a look at some more arguments next time. I'm going to leave you with some arguments for you to try yourself. These are all valid, so all of your trees should be closed by the end. But have a go of them. Have a go at these. See what you come up with, and we'll have a look at some more stuff next time. We'll do invalid arguments, I think, maybe. Okay then. Well, thanks for watching. Goodbye.